Welcome back. In our last unit, we mastered the engine and the oven, the hardware that moves the air. But today, we address the track itself. Imagine running a race on ice wearing sneakers, or on sand wearing spikes. It doesn't matter how fast your engine is if your tires can't grip the surface. The GC column is the heart of the system. It's where the stationary phase coatings interact with your volatiles. Today we learn the strategy of matching chemistry to goals to achieve peak perfection. Have you ever seen peaks that merge into one giant blob? That's not a hardware failure, it's a chemical mismatch. As a specialist, you need to understand that the grip, the interaction between the molecule and the stationary phase, must be precisely tuned. If the grip is too weak, everyone crosses the line at once, coelution. If it's too strong, the race never ends. We must choose the right surface for our molecular tires. To master column selection, we follow 4 sectors. Sector A, the evolution of the tube, understanding why we moved from packed to capillary. Sector B, the polarity handshake. The core, dissolves like chemistry. Sector C, the triple constraint, how dimensions affect your resolution and runtime. And Sector D, the silent noise managing column bleed to save your mass spec detector. Packed columns were great for the pioneers, but they were the standard definition of chromatography. Today, we use wall-coated open tubular, WCOT columns. Because the center is open, we can have 60-meter columns with minimal resistance. This allows us to achieve incredible resolution. A pro chooses WCOT for mass spec because it minimizes the amount of liquid phase that can bleed into the ion source while maximizing the plates per meter. The polarity handshake is your most strategic decision. If you are racing non-polar hydrocarbons, you want an ice rink, a non-polar PDMS phase. But if you have polar sticky molecules like phenols or fatty acids, they will fly right over an ice rink without separating. You need a sticky floor, wax or polyethylene glycol, to slow them down and force them to compete. Matching the polarity is how you achieve peak separation in minutes instead of hours. Look at this decision matrix. A technician uses the column already in the machine. A specialist looks at the functional groups. If you're analyzing FAMEs, fatty acid methyl esters, you move to a PEG column. If you're looking at environmental PCBs, you might need a cyanopropyl phase. By choosing the right chemical grip, you ensure that even isomers with the same boiling point can be separated based on their electronic character. Here is a hard lesson from the lab. A student comes to me and says, "My peaks are overlapping, I need a 60-meter column." I tell them no. Doubling your length doubles your analysis time and your gas cost, but it only gives you 40% better resolution. It's a diminishing return. A pro knows that before adding length, you should decrease the internal diameter, ID, or change the chemistry. Adding length is the most expensive way to solve a resolution problem. Column bleed is the background nightmare of MS detectors. As the temperature rises, the polymer coating starts to peel away at the molecular level. This creates a rising baseline in your chromatogram that can bury trace signals. If your background looks like Nager/Z207 or 281, that's your column talking to the detector. A specialist uses low-bleed MS-certified columns and conditions them overnight to ensure the noise doesn't kill the truth. Look at your chromatogram. Are your peaks sharp mountains or broad hills? Tailing peaks, what I call shark fins, tell a story of struggle. They indicate that your molecules are getting stuck on active sites on the column walls. This usually means your column needs a chemical makeover through derivatization, as we learned in Module 2, or that your film thickness is too thin for the concentration of your sample. Peak shape is the ultimate report card for your column choice. Summary: matching chemistry to goals. Today we've moved from the architecture of the tube to the polarity handshake and the triple constraint of dimensions. Remember this mantra: don't just pick a column because it's already in the machine. Pick it because the chemistry demands it. You are the architect of this race. Don't leave your resolution to chance. Precision isn't about the machine. It's about your mastery over the stationary phase. We have mastered the column for things that turn into gas easily. But what about the things that refuse to melt or dissolve? How do we handle solid plastics, rubbers, or polymers that would break a traditional injector? To handle the, quote, unvaporizable, we need to break the molecules apart before they enter the race. We need to go from surgery to brute force destruction. Let's prepare for our next strategic challenge. You've mastered the coding for volatiles. But join me in our next unit, Module 4-3, Cracking the Solid, where we utilize pyrolysis GC to analyze polymers and rubbers. We've managed the race. Now let's learn how to break the rules and capture chemical fingerprints from things that weren't even supposed to fly. I'll see you in the next module. Any final questions on column polarity or bleed before we move into the oven's dark side?